My name is Caleb Smith. I'll be giving an introduction to Celery. And if you want to follow along on your computer, the links are at that bit.ly URL. I'll leave it up for just a moment. 1K1F, capital V, capital L, Z. Sorry, I didn't make a friendly one. Okay, so just a little bit about myself. I work at the Cactus Consulting Group. We're in Carborough, North Carolina, soon to be Durham, North Carolina. We're moving, the city's not. Anyways, I mostly program in Python and JavaScript for work. Sometimes I program in C and Scheme and some other stuff. I enjoy music theory and teaching. You can look at my GitHub at Caleb Smith, and I'm on GitLab as C Smith. I think I only have one repo. And I'm on Twitter as Caleb Smith NC. So, what is Celery? It's a distributed system for processing messages on a task queue. And it has a focus on real-time processing and support for task scheduling. So this talk will give a high-level overview of Celery uses, what some of the setup choices are, and what some of the early stumbling blocks are that you're likely to encounter. Along the way, while I'm talking about setup choices, some of it gets slightly detailed. There are a lot of sort of different things to consider about your project when you're making those choices. So if any of that is overwhelming, realize that at the end, I will give my prescriptions for what I think, if you're just starting with Celery, this is the list of configurations you want, sort of the sort of sane default for a beginner. Okay. So the major features of Celery, it allows for out-of-band processing, and this processing can be started periodically, sort of like a cron job, or it can be triggered by web requests. It can also be triggered by other tasks. So tasks can produce other tasks on the queue. It communicates with a message broker, and that distributes the work. So your Celery workers might run on one particular machine, but there is kind of a distribution method built in by using a message broker. You can distribute it however you need. It can act as a cron job replacement. Also, it can help ensure requests are timely. So if we have a lot of processing to do and a web request comes in, we can kick off a task to be run asynchronously, and we can give a response immediately rather than taking a web request, doing a bunch of work synchronously, and then returning a request. Essentially, we want the user to not have to wait for us to send an email or generate thumbnails or any number of things that we need to do, but maybe not while they're waiting for a response. So it's reasonably good at distributed computing and high availability. And so I think that Celery helps solve a sort of common use case for those things, especially in web projects written in Python. I don't necessarily think it's the be-all, end-all of distributed computing and high availability. That's not to complain about it in any way, but there are certainly certain use cases that if you want to use Hadoop or Erlang or Go or I don't know, those things might be a better fit for certain distributed computing needs. But Celery satisfies a very common use case, and we'll talk about those momentarily. So a little bit about the history of it. It was initially released in 2009 with version 01. In the next year, 1.0 was released. Several improvements are made. Not a whole lot of major changes to note historically. 2.0 came out later that year, and lots of different tools and sort of features were added. And the most notable thing in my mind is that it's no longer Django only. I do a lot of Django, and I like it just fine, but originally Celery was kind of tied at the hip with Django, and now you can use Celery with Pyramid, Flask, kind of whatever. It's agnostic to any sort of web framework. In 2012, version 3 came out, and it has a lot of performance improvements. Some of those are in terms of speed. There are also some sort of reliability improvements in terms of how it handles forking and some different things. And it also has a more simplified API, in my opinion. One thing to keep in mind as well is that these various changes, like for example, if you picked up an old project that was written with Celery 2 and you want to upgrade it to Celery 3, there is a doc that's called What's New in whatever version, and it's pretty good. There's usually some backwards incompatible changes with the major version upgrades, but they're pretty reasonable. Yeah, you can read through it and figure them out without too much work. 3.1 came in 2013, and that's the one I probably have the most familiarity with. Most projects I work on, we're using Celery 3.1. And so pickle serialization is deprecated. That's something we'll talk about later. I think the improvements in 3.1 will only make sense unless you already have some familiarity with Celery, or until we talk about some of these things. Also, the CLI program, the various command line interface programs that Celery comes with are now all under one Celery command. So you have Celery, and then it has subcommands. In other words, you used to have Celery Mon and I don't even remember, Celery CTL, lots of different programs. Now they're all under kind of one umbrella. So to look at some sort of boilerplate for how you get Celery set up in your project, this is kind of what it looks like. And in my examples, I'll mostly use Django, partly because that's just kind of my experience and kind of what I'm most familiar with. But anytime you see Django stuff, like, just kind of bear in mind that there's no longer any kind of dependency with regard to Celery. You can still use any other frameworks. So here I'm essentially importing a settings module from Django. I'm importing this Celery class from Celery. This app equals Celery, etc. This is sometimes called the app instance or Celery instance of a project. You can have more than one. It is generally a singleton. You usually have one, and it is the configuration for the whole project. You usually only need more than one if you have some special needs, but for starting out, you just make one. So essentially, the first argument there is a string. That's just the name of the module it's in, and the broker argument is the URL of the message broker it's going to attach to. The config from object is a way that you can pass it a module for it to load its settings from, and then the last bit, the auto discover tasks, is a list of modules that it will use for task discovery. So task discovery you can think of as being analogous to test discovery, like with nose. And Celery used to have a way that it did task discovery that was similar to nose, where it would just kind of do it automatically and you didn't really think about it. And with this auto discover tasks, which is a fairly recent addition, now you have a mechanism to kind of control that if you need to. So from the command line to run Celery, once it's set up thusly, you just type in this last thing here with Celery-A and so on. So that app name just ties directly into the string we've provided there. And the worker is the subcommand for running the Celery worker process. Now, if you are using Django, there is a Django Celery package. It comes with a setup loader function that you call that basically does this. And so if that's, it kind of has these as the same defaults, and you don't quite have to do it this way. But I kind of wanted to show what the boilerplate was more in general. The other web frameworks, Pyramid and whatnot, also have Celery integration libraries that you can use. So as part of our sort of, after we see the boilerplate, I wanted to have a simple example of kind of when you might be building a web project and say, maybe I need Celery now. If I didn't have it before, maybe I need it. So here, we basically, we're importing this kind of made up make thumb function just imagine it's Swirl or ImageKit or whatever, and all it does is we give it an image, and we give it a size, and it makes thumbnails for us. So here we have a model that, for the purpose of this example, is basically the user makes some sort of post. And in that is an image field. So the user can upload an image. So this thumbnail sizes class attribute I've defined, this is a list of, width height parameters, right, for the different thumbnails we want it to make. And then in this save method, we're just iterating through that and saying, okay, we're going to make a thumbnail for all of these in the list. And so, you can imagine that you have this kind of trivial bit of code in your web project, and it works fine. And then, as requirements often do, they change, right? So it was working great, and then they said, yeah, so instead of that one thing you did where you made a thumbnail, I kind of need you to make 10 or maybe 20. Well, that gets kind of tricky, right? Because I don't know how, particularly fast one of these might be, but you can imagine that there is an upper limit, right? So if it takes a couple seconds to make a thumbnail, we don't want to wait, 10 seconds or more. Or rather, we don't want to make the user wait. They've uploaded their photo. We don't want to twiddle our thumbs, make a bunch of thumbnails, and then give a response. So instead, we need to handle the thumbnail creation asynchronously. So here, from our project, I'm importing a thumbnail tasks, or from that module, I'm importing generate thumbnails task, right? So we have a task that generates thumbnails. And so now in our save method, instead of looping through it, we just say, okay, here's the task name, and put .delay, and then we pass it the arguments. So the first one there is, the path to the image, and then the list of sizes. So essentially, our task is now what's going to happen is the request comes in, the user's created this, it gets saved. When it gets saved, we call this task to be run asynchronously, so it's put on the queue. We're going to generate the thumbnails, but we can immediately give a response to the user and say, hey, we got your photo of, babies, whatever. So to see what that task looks like, it's really just as simple as we import that app instance we built earlier, and it has a task decorator attached to it. So we define a function, and we say @app.task to make it a task. And then within our task here, you can see we just loop through the sizes and call this make thumb function. So it's pretty straightforward. It's really just a function with a decorator that gives it the ability to hook into Celery so that we can run it as a task. So more broadly, what might you need Celery for? Generating assets after an upload. That's what we just looked at, right? The user did some action, they needed to upload something, and we needed to generate some more assets, thumbnails, or who knows. Another thing that's common is notifying a set of users when an event happens. So you can imagine some forum, for example. There's a thread, a post thread on a forum, and someone says whatever, and maybe you want to notify all the users that are on that thread that there's a new post. If you do that synchronously, again, you're kind of stuck with, well, now I need to notify, 10 or 20 people, and, I'm making this person that is posting something on the forum wait. So you probably want to avoid that. Keeping a search index up to date. So if you're using Solar or Elasticsearch or some other search index, it very commonly needs to make a lot of database queries as part of, what it does to create that index. And as you change data, you need to keep the index up to date. So if you can do that asynchronously, again, that's kind of a good use case. And replacing cron jobs is another common one. I don't necessarily know that, or I wouldn't necessarily say that, in all cases that you would want to use Celery in the place of cron jobs. But if you're already using Celery for these other things, or if you want to use some other mechanisms, it's totally a good use case to use Celery for these sort of periodic things.
What would be
Yes.
a case where you would want to use Celery opposed to cron jobs?
Sure. So one would be that we have,
Repeat the question.
yes, oh, sorry. Yeah, to repeat the question, he asked, when would you want to use Celery in the place of cron jobs? I would say that you certainly don't have to. I think it's simpler if you're already using Celery for these other things, so that way you have the same mechanism that's doing the periodic work as opposed to some other part of the system. I also think that Celery is maybe a little easier to deploy than cron jobs. I think that it's not that it has to be, but often cron jobs are kind of these forgotten thing that some system administrator put on the box, and they sort of work, but they might not be in version control, and there might be some detail you forgot along the way, and it's kind of, they're harder to test and that sort of thing. And I would say testability is another thing that, maybe your cron job just calls Python code, but a lot of times cron jobs are, kind of complicated and have a lot of bash code, and they're kind of hard to test. So there are many setup choices. When you read the Celery documentation, it's somewhat reminiscent of the Arch Linux documentation. You say, well, I don't know what a bootloader is, but it describes 5 different ones. I don't know which one to pick. Well, it's sort of like that, but hopefully I'll help you navigate through that. So there are a few different choices. One is that Celery uses a message broker. Another is that it uses a result backend. You can also choose not to use a result backend. And it uses a concurrency solution. So that being, it either uses multiprocessing or green threads. And these are kind of the major setup choices that you'll encounter. So the role of a message broker and how do we go about choosing one? So the message broker stores tasks on queues, and it allows workers on the different either processes or machines or threads to produce and consume these tasks. The broker stores the data that answers the question, what work remains to be done? So the Celery, Celery supports several different brokers. The main ones that you'll see are RabbitMQ and Redis. So there are many others. Not all of them have a maintainer. And so essentially RabbitMQ and Redis are kind of the most supported ones. They support monitoring, and so forth. Some of the others lack certain features like monitoring. RabbitMQ is the most robust solution. So if you need to have some serious infrastructure for what you're doing, RabbitMQ is kind of the answer. So to kind of understand more of what the message broker does and why I think RabbitMQ is the more robust solution, I want to look at in detail a little bit of how Celery works and how it works in conjunction with the message broker. So first, this producers is anything that can produce a task on the queue. So that could be a web request, it could be a periodic task, which in the background runs and every 5 minutes it puts a task on the queue, or whatever interval. And it can also be a task itself. As a task executes, it can produce a task onto the queue. So tasks are first in, first out. So, if this producer produced 6 tasks, then, this one on the far right will be is the first one put on, it'll be the first one that's executed. So the consumer is a process that's run, it's part of Celery. And the consumer's role is to consume tasks from the queue. And in the little box, I have 4. And in the sort of default configuration, it pulls 4 off at a time. So it sort of has like a little buffer where it stores these tasks before it delegates them to the worker pool. Now, before I go into further detail, I need to remember that in this diagram, I'm assuming all default configurations, and in a moment I'll unravel, a few of the details of things that you can tweak. So by default, it consumes 4, and when tasks go from the broker and go into the consumer, they are considered to be in a pending state. So now, what happens is when in the worker pool, you have either several processes or threads. These workers are doing work, And when one is free, it is given a task from the consumer. At this point, the task enters the started state. So that means that a worker is executing that function, essentially. Now, when a task enters the started state, the consumer sends a message to the broker to acknowledge that the work has begun. And I say acknowledge because with RabbitMQ or an AMQP broker, there's an idea of message acknowledgement. And so I'll get more into detail on that in a moment. So essentially, the task becomes acknowledged, it enters a started state, and it enters a worker in the worker pool. These workers, you can think of them as gears. Some people think of them as lemmings. They do work, and generally they have side effects. So in the case we saw earlier, we produce thumbnails. Another common case is they do some work, and as a side effect, they write some data to the database or update the database. So when they're done, they enter the success state if they worked, or if an exception was raised, they enter the failure state. Now, at that point, they go into the result backend, if we have one. So the asterisk there is me indicating you might not have a result backend, in which case the little brown pixels just fall off the diagram and we just forget about them. But if you have a result backend, that's where it gets stored. So the result backend stores that the task succeeded or failed, and it also stores any the traceback of any exceptions if you had them, or if your function returned and it returned a value, as in the keyword return. If it returned something from the function, that data gets stored. The task we had earlier implicitly returned none because I didn't use return, right? Okay, so RabbitMQ, or Celery rather, was created with RabbitMQ in mind. And RabbitMQ implements the AMQP, I almost said AMQP protocol, it's redundant. So it's the asynchronous message queuing protocol. And so it tracks message acknowledgement. And that's one of its major differences from some other messaging queues and things you can use as brokers. So essentially, in a very gross oversimplification, RabbitMQ is the Postgres of message brokers. What I mean by that is it cares about maintaining the integrity of your tasks, and it cares that the message was acknowledged, and it tracks if they go unacknowledged so it can try them again. So essentially, if your Celery consumer is running, something bad happens, and there's a power failure or something, those tasks are marked as unacknowledged, and they will be retried. So, or rather, they'll be sent to a consumer yet again when a consumer is ready, and they will be run. So that way, essentially, you don't have data loss. That's kind of the long and short of why I say you should use RabbitMQ. You want to avoid data loss. Yes?
Is it also true if the Celery service itself crashes? Is there persistence there?
Yes, great question. He said, is it also true that if the Celery process itself terminates, that the task is maintained? Is that what you said? Okay. Yes. So essentially, when the consumer grabs this task from the queue, the broker still knows about it, but it's no longer marked as ready. It's marked as unacknowledged. So it's aware. Essentially, the broker is aware that the task is in this state in which it's not being worked yet, but it shouldn't be given to another consumer. And so in that way, if the consumer dies, the message broker knows that it has unacknowledged tasks, and it can put them back into the ready state and try them again. So, excellent question, and honestly, I think that's the summary of why you should use it. So you can also use Redis as a broker. And it uses the pub/sub capabilities with what's called ACK emulation, and you'll see ACK emulation mentioned in the documentation. ACK emulation means it's a way of emulating the acknowledgement behavior that AMQP does. But it is emulated. So there are some caveats if you use the Redis broker. So Redis, is a key value store, And so if a consumer shuts down gracefully, specifically if it receives a SIG int, then the consumer will actually send the messages back to Redis. And then Redis knows, because of its emulation layer, oh, these are unacknowledged messages. So I'll keep track of that. Otherwise, they're gone forever. So in the case of the earlier question, somehow the consumer dies, something bad happened, now it's gone forever. Oops. So as part of its accumulation, it uses a timeout to determine successful delivery to a worker. And this is called the default visibility timeout. In other words, it's never quite sure that the task got there and that it's being processed and so forth until this timeout is up and it hasn't received a message to say, hey, this failed or something. So by default, that timeout is really long. It's a few hours, I think 5 hours. So the detection of when that failed is often really late. Another issue with that, I'll get into in just a moment. So you want to configure the default visibility timeout carefully. So in the case where I have a task that actually takes 20 minutes to complete, if my default visibility timeout is 10 minutes, then all of a sudden I have a task that's running too long and Redis thinks it never completed or that it will never complete. So it will send it again. So now you're running it twice. In the case of a database backup, well, you're probably hurting your performance a little, but it's okay. In terms of correctness, great, now you have 2 backups. Who cares? If it's a Dogecoin exchange or, I don't know, something with banking, it probably matters a lot. Another thing about Redis broker configuration is that you want to configure Redis to avoid key eviction. It does a bit of kind of cleanup as it runs, sort of vaguely garbage collection. You don't want it to evict your tasks and whatnot. So there's a bit of configuration that is described in the documentation. If you use this, you want to use you want to configure it to avoid key eviction. So in summary of that, the sort of essence of the Redis broker distilled into some distinct facts. If you're using the Redis broker, you might process a task correctly in the correct order. You might also process it several hours late and not in the original order. You might process it twice or more, or you might never process it. So yeah, that kind of bothers me. I don't like that idea. So, if your use of Celery, if you know for a fact that you only, are doing things that, if this, this is okay, that's fine. If you don't know that for a fact, I'd say use RabbitMQ. So the Firetruck contingency plan have multiple RabbitMQ nodes in a cluster configured with high availability queues. This gives you leader-follower replication. The replication is for redundancy. It doesn't actually load balance for performance or anything the way like a database does. But this means that if a Firetruck hits one of your RabbitMQ servers, you still have all of the correct data on another server. Just a quick example of how you wire it up. You pass the broker URL in there, as we saw, and this is what the broker URL looks like. The first one being for Rabbit, AMQP, and the second is, if you're using Redis, that's what it looks like. So, a result backend, tracks the state of the tasks. That's the pending, started, etc., and the return values or any exceptions from when it. So it essentially stores a mapping of a task ID with a result. And each result backend has strengths and weaknesses, caveats. So to see what it looks like in action, this is a simple example from the docs with just an add task. It's kind of a silly, trivial thing. And so...
And the microphone closer to your mouth.
Okay.
Yeah, good, thanks.
Okay, there we go. So with this, we can keep track of the results. You can see we have the result ID. and at the end, we have a value. Now, this can be used for certain specific things, especially if you want to keep track of that ID somewhere in your web project and check on its state later. But in general, are you not impressed? Yeah, I'm not, because you probably don't need a result backend. If you're just starting, don't worry about it. Now, there are a few that, different ones. So Django Celery comes with a database backend. SQL Alchemy comes with one. They do offer a quick and simple monitoring solution. So essentially, you can look in the Django admin and see that this stuff is executing correctly or not, and that sort of thing. I say monitoring with quotes because it's not a robust monitoring solution. It's not like you have Nagios and all these different things. So for monitoring, there is a project called Flower, and there are a few other such projects that offer great monitoring of Celery. The database backends also, if you have high task granularity, they can be very heavy. So essentially, if you're writing to the database every single time a task returns, there's a performance cost. There's also an AMQP backend. It spawns an Erlang process and creates a new queue for each task. This is very expensive. Just yuck. I really honestly don't know why it exists. So it turns out that a key value store is well suited for a result backend. So earlier, I don't want to just pick on Redis. It works great as a result backend. But a database or RabbitMQ will work. But a cache is a natural fit for that. So just as an example, this is what you can put in your configuration. You essentially, Celery result backend, and then you have a URL to it. So you also have to consider a concurrency solution. So the options here, between multiprocessing, so you run multiple worker processes, or green threads. So you run a process and it has several workers that take turns in an event loop. So the multiprocessing, you'll see in the documentation, people call it the pre-fork pool. But anyways, that's just, you have a consumer running as a process, and then you have lots of workers running as a process. They use inter-process communication to do their work. Then there's also eventlet and gevent. And these are both green threads. They use different underlying libraries. They have some differences, but the general approach for both of them is that they use green threads. So with green threads, you have some performance advantages, especially if you're I/O bound. It does require monkey patching, and it might not work with your existing code, and especially with your dependencies. So if you use it, you kind of need to figure out if that's the case. If everything you're using can do async I/O and is monkey patched correctly. Essentially, the tasks need to not block I/O, or you lose absolutely all concurrency because you have one process and something is hogging the ball. Now you're stuck. So again, performance advantages, there are some, but you have to make sure it's not going to just fall apart. With multiprocessing, it's simpler in the sense that that's not going to happen. The recommended number of workers is usually n+1, where n is the number of cores. So some machine has 4 cores, you're probably going to run 5 workers if you're using multiprocessing. The disadvantage here is that you do use more RAM because each process has its own RAM and so forth. And so to see what that looks like, when you run the worker, essentially it's this -p argument. So the -c is how much concurrency you want. So in the first example, we're using the default, which is multiprocessing, and we're saying, okay, I want 5 workers. In the next one, we're using eventlet, and the last one, we're using a gevent. So both of those, you can see that just as a value in there, we've got a concurrency of 1,000. Now, of course, that seems to be 200 times faster than the concurrency of 5. But one of the things to think about there is that depending on what they're doing, that might mean 1,000 concurrent connections to your database, or an attempt at 1,000 concurrent connections to your database. So we can't essentially turn a dial and say, great, now it's faster. You kind of have to consider what the tasks are doing with regard to the concurrency. So measure, so forth. Now, I'll get into that a little bit with the optimizations. So Pitfalls. There are a few different ones. One is in regard to parallel safety, also task granularity, and misguided optimizations, which the last one I think almost goes without saying. We always know about misguided, premature optimizations, right? So parallel safety. You want to write tasks to be parallel safe. You have no idea when they'll run, and you need to plan for this. So if you try to disallow certain tasks from running in parallel, you're kind of focusing on the wrong problem. Now, granted, that's not to say you can't use some locking mechanism or rate limiting and whatnot, but if they fundamentally do the wrong thing, if they run in parallel, then you need to address that in the code. So you also you want to use database transactions where needed. You essentially don't want your tasks to do lots of different things to the database without a transaction, and then it's running in parallel with another one. You can get into some. You generally will want to wrap all of that in a transaction. So this last one, I think, if you're new, is maybe not expected, and that's don't pass objects as task parameters. So the reason I say that is the default way that your tasks are serialized is to use pickle. And while you'll hear about security concerns with pickle and whatnot, one of the other concerns in this particular case is stale data. So if I call a task and I pass in an object and it's some instance from my database or something, by the time the task runs, that may not be the correct values. But because I've passed in this object, when it gets deserialized, well, it's in the state it was when I called the task, when I put the task on the queue, right? So instead, you want to use something like a unique ID, right? So here, as an example, I have a PDF report. So the report here that I think is kind of important is this create PDF from HTML. It's really just imagine it's a function that takes some HTML, it generates a PDF. It uses some library to do that. And more than likely, if you've done this before, you realize that can be slow. If it's 1 or 2 pages, it's fine. But often, if you're making a PDF and it's a big report, well, that gets kind of scary, right? So this is probably a good candidate for a Celery task. So in this task, it takes a report ID. Notice it doesn't take a report instance. We take the report ID and we retrieve it from the database. So in so doing, we get, the report that is most up to date. In other words, the report as it stands when this task runs, not when it's called. That's important. Or else the next part fails, which is this guard. So if the PDF last modified is less than the HTML last modified, essentially we know the HTML has changed since we've last changed generated the PDF. So then we call this function to generate the PDF. It might take a long time. Then we, this now equals datetime.now, we get the current time. And then at the last moment, we update the report so that it has the new PDF data, but also it has this new time. By doing the last modified, now if this task gets kicked off in parallel, our code will do the correct thing. Because the first one will run, and it will update that the time is, now, when it finishes. And then the next one, if it comes through, it'll say, this is already done. If they run in parallel and they both pass the guard, one of them wins. Doesn't really matter. So you kind of have to think about those cases for parallel safety. So note on Pickle, I kind of talked about this with serialization. So you don't want to pass arbitrary Python objects, although it will allow you if you use the default that is now deprecated. So you want to pass values. So those values might be integers or strings, or you can also use lists and dictionaries. So for serialization, you want to use JSON or YAML. I think there's some other options, but generally you just don't want to use Pickle. Poor task granularity is another concern. You want to choose right-sized tasks. If they're too big, the code is hard to maintain, just like any other code. But it also is harder to scale horizontally. You lose all concurrency. You're running a task and it takes 30 minutes. Well, now you can't parallelize it, right? Now you can't break it up and run it, smaller parts of it. So you want to generally think the single responsibility principle. I don't think you have to, take that completely literally, but it is good for tasks to have, smaller granularity. They might just send an email or a tweet or something, not, long lists of stuff. You don't want to send, thousands of emails or net requests in one task. So also, this functions does not equal tasks. Well, the tasks I showed you so far are just functions. They are decorated. Yeah, okay. But what I mean by this is don't let the interface affect how you program it. So what I mean is, as an example, a database model in most frameworks is a class. That doesn't mean that that's that your interface to the framework defines how you structure your code, right? A database model might call other functions and import things and do things that aren't just that class. So in other words, if your task is a function, it doesn't have to be just one giant blob of stuff because, hey, this is how I hook into the framework. Now, you want to design your tasks around these small units that can execute simultaneously. So you can't just parallel all the things, right? So some tasks are essentially like frying an egg. It's inherently sequential. You have to crack the egg and then fry it. There's kind of a series of steps. But you can fry more than one egg at a time in one pan, right? So in other words, I might query the database and determine that I need to send 1,000 emails. I can send those emails in parallel, but to first know which ones to send. So part of that is sequential, and part of it I can parallelize. So each task has a small but non-trivial storage and network cost, right? So if you have many tasks and you have a very small worker pool, your queues can fill with tasks and essentially, you get a backlog, okay? There are a few considerations you can, configurations you can do to kind of help with this. One of these is called the Celery prefetch multiplier. Earlier we were looking at which pulled the tasks off the queue. With the Celery prefetch multiplier, you can tell it, I don't want you to just consume 4 at a time, I want you to consume lots. So if you have small task granularity, you can get lots of tasks into that consumer, and then you can divvy it up, and it'll be more efficient if you have small granularity. So I would generally say you want to look at configurations for performance problems before you necessarily try to optimize code, unless it's just really obviously bad. Beyond that, though, if your tasks are really small, you can consider building them into what I call chunks. So in other words, a task that maybe writes 5 things to the database instead of 1. So that way you don't have way too many. So here's an example of the granularity problem. We have a forum post. We determine all of the users that have made posts on that thread, and then we need to notify the user. So here, this task will go through this loop. This might be fine for a small site. If it's lots and lots of them, then we want to notify the users as a task. So instead, we call notify user task.delay near the bottom there. And essentially, now we're notifying those users asynchronously. So if we have many users on this forum, then the first one we call, it determines what needs to be done, and then we queue up all of the actual notifications. And those notifications might be SMS or email or something. Okay. I'm just about out of time, so I'll just very quickly say, most of these premature optimizations, I feel like I've kind of gone over the last little bit. Look for configurations for easy win. Otherwise, look at task granularity. I have a complete example you can review on your own. It's an example of a Twitter bot that does some different stuff. I want to walk through it, but there's no time. Essentially, it's a Twitter bot that we use for Duckling US. There's some simplifications. It's not the exact code, but essentially, we send different tweets, and this first one is called when a new outing is created. We send an announcement tweet. When periodically, we send reminder tweets, and we check what are the outings that are upcoming? Let's notify all of the participants. Notice that the tweet task is its own task that we put on the queue. So essentially, this first one is called from a web request. This one is called periodically. And then this is how we configure the periodic interval in our settings. It essentially, with this scheduled time delta 5 minutes, it'll run every 5 minutes. And then our tweet task, it essentially takes a message and sends a tweet. The only, I think maybe sort of not obvious thing here is if it succeeds, it updates the participant to say that the reminder was sent. And so that way, when we are determining who to send reminders to, and we're looping through the participants, we check, right, when we create the participants list, right, this filter has allow reminder equals true. Sorry, I didn't realize this was going off the screen. We also check reminder sent as false. So people that haven't been reminded yet, we don't want to remind them twice. That's kind of annoying, right? So prescriptions, which broker use RabbitMQ if task data is important. Otherwise, Redis is fine if you understand the caveats. Result backend, you likely don't need one. Just, until you have some advantage, need one, just forget it. It's just whatever. Just forget about it. Concurrency solution, use multiprocessing unless you know you won't block the thread. If you've tested it, you understand, what can happen there, just use multiprocessing. And, review the pitfalls we talked about. Don't use pickle, start small, and, profile stuff, change configurations. Thank you.
Would you put up the earlier slide you had with URLs?
Sure. This one is, this one?
I think after that one.
I'm sorry, I'm trying to think of which, maybe it was,
Maybe it was that.
okay.
So I guess there's time for one question.
Sure.
Hey, and I might have to follow up with you after the talk. When you could set the parameter for taking setting the number of tasks that you're taking off of the queue,
Yes.
And then you're sending those to individual worker processes. Is there any way that you could send more than one set of task parameters to one worker process? So a worker process needs to execute multiple items that are within the queue, opposed to only one item at a time.
Right. Great question. There is, in my mind, there's kind of a mechanism to do that, but it's not at that configuration level. It's kind of the way that you structure the code, and you can essentially, some of it can use callbacks, but it's essentially that type of mechanism. Call this task. When it's done, it's going to call a task. If you kind of want that, like one thing after another, but I don't. To kind of address your question a little better, I don't think you can do it at the level of, one worker gets this set of tasks. Exactly. So, and that's kind of where the chunking thing came in. Mm-hmm. So sometimes you can structure your task so that it's kind of chunked, so that the one task actually does 5 things. Thank you.
Okay, if you want to continue on, grab Caleb outside in the hall, and you can move to an open space.
Sure. Yeah, I'll be in the open space. That'll work. Thank you.